And that in a medical device saves a tremendous amount of time because you don't have to do a gauge R&R on it, and you don't have to do an IQ, OQ, PQ on that feature, and you don't have to build 3 lots of parts and measure all those features, which is a lot of times a waste of time.
Hello and welcome to another episode of the Being an Engineer podcast. Today, our guest is Edward Jaeck, a distinguished engineering professional with a robust career spanning over 2 decades in design, manufacturing, quality, and program management. Currently, Edward serves as the President of SINE18 LLC, where he provides strategic guidance in manufacturing and quality to various clients. His previous roles include Vice President of Operations at Quality, as well as Vice President of Strategic Growth and Business Development at Lowell, Inc. At Medtronic, he held roles as a Principal Component Engineer and Principal Design Assurance Engineer. Edward's experience is further highlighted by his tenure at Intel Corporation, just down the street from us, incidentally, where he managed significant R&D projects and contributed to the development of numerous patents in electronic packaging. Lastly, Edward conceived and patented a reconfigurable vehicle body and truck bed. Edward, welcome to the show, and thank you so much for joining us today.
Yeah, great. Thank you for having me.
It was cool that I saw Intel on your resume, where our facility here at Pipeline is in Tempe, Arizona. Those of you who are not from Arizona, it's just outside of Phoenix, and Intel is just right down the road. So that was kind of a cool connection to see right off the bat. And I think you spent some time at ASU as well. Is that right?
Yes, I have an undergrad in mechanical and a master's in industrial engineering from ASU.
Terrific.
Great memories, man.
Yeah. It's a little warm, but cost of living is low, and the winters are gorgeous here.
Yeah, we were just there this summer with the kids in June, and I thought I was going to lose half of my family at the 12 o'clock walk back from the MU to the parking garage. I said, okay, folks, we got to pick up the pace here. I'm losing you.
Yeah, it gets very warm. It's, let's see, right now it is 106 degrees. Today, the high is only going to be 108, which is not terrible. We've had some 115 degree days here recently, but we get through it somehow.
Yeah, it wasn't bad. I loved it.
Well, you did your schooling, your education at ASU, prior to attending the university. What was it that motivated you to explore a career in engineering?
So I built stuff. I grew up in upstate New York, and I built stuff and finagled stuff, and we had friends that were handy and some farmers and some other guys that were rich guys that had toys. And, a couple of us just were hands-on, and we messed with stuff and innovate and do some fun. Like I had a buddy that he ended up becoming a mechanical engineer, and he got the great idea that we should ski behind a snowmobile. So we thought that was a great idea. So we built some instruments to do that. And, of course, that led into jumping off the skis and jumping a pipeline that we had. And it,
wow.
Yeah. When you're around somebody that's creative and handy, innovation and creativity take off.
That's a really cool idea. I'm not sure I've ever seen or heard of that before, but now that you say it, it seems like, well, yeah, why wouldn't you do that?
Well, we had a pipeline. I lived near a reservoir for New York City, right? So a lot of New York City is fed by reservoirs upstate, and they're all gravity fed. Right. So it's a huge undertaking from the early 1900s to build these things. So you can imagine that above ground pipeline it's a trapezoid, which is probably a 12 or 20 foot diameter pipe buried in it. So all the way from, our house 100 miles north of the city, all the way down to New York City, there's this pipeline, right? That was built back in the 1900s. And it's tall. In places, it's 20 feet above H equals 20 for those engineers out there. But it's a trapezoid, so we could put the snowmobile on top of the trapezoid, and you could take this ski rope from water skiing, and you could ski alongside the trapezoid. And when you wanted to cross over the trapezoid, now the width at the top was probably 12 feet because you could drive a truck up there, and you could jump from one side of the trapezoid to the other behind the snowmobile, right? And then at the end of it, there's a big flat, and of course that's where we built the jump. And I've got pictures where we're coming down, probably doing 20, 30 miles behind the stone bill, and you let go of the rope and there's a jump, and I have a picture of my buddy 6, 8 feet in the air. Skis
wow.
just landing in 2 feet of powder, right? Just crazy.
That's fantastic. How cool. What a fun idea.
He's a brilliant man. Brilliant man.
Well, that eventually led you into engineering, and you've done a lot of things in your career. Let's maybe start current, and we'll work our way back a little bit after that. So you own a company called SINE18. Tell us a little bit about SINE18. Why did you start the company? What's your focus there, et cetera?
Yeah. So first, SINE18 is spelled SINE for the engineers out there, like sine, cosine. So SINE18. People ask, where'd the name come from? Came to me in a dream. And if you do the derivation of that by hand, you get into all sorts of identities and phi, the magic ratio kicks in. Ironically, most ramps, loading docks are 15 to 18 degrees. So there's a lot of things that end up in this 18-degree space. Just SINE18 just came to me. But what's interesting about SINE18, if you remember your trig in the circles, you say SINE18, I say cosine 72. It's the same thing. Right. So in consulting, it's a great reminder that there's more than one way to look at problems. Right. And there's everything in between. So SINE18, I start with strategic planning, because that's kind of what most small to medium companies are horrible at. And my joke with people is we all need an advocate in life. Right. And I could be great at some things, but can I do it well myself for my business? Probably not. Right. So what I focus on is strategy. And then with the strategy, then I jump into manufacturing and then quality, right? And data-driven decisions, which are really my strength areas. If you don't have a good strategy, then it's a waste of time.
We're going to get into that with you a little bit later, because we want listeners to derive some legitimate value from these conversations, right? We're not here to, plug one business or another. We're here to extract useful information from the engineering community and put it all into a central repository where other engineers can receive and learn from that information. So I'd like to dive into the strategy with you a little bit, especially for those who are in leadership roles or maybe thinking about starting their own engineering company and how they should go about the strategy of the business of engineering. But before we get to that, let's talk a little bit about some of your previous experiences. So Intel, Medtronic, and Lowell. Share a little bit about those companies and how they shape your approach to the growth and kind of the quality management at SINE18.
So Intel was fascinating. For those junior engineers or new engineers, if you can get into a big company early, really consider doing it. You don't have to stay long, but you have an opportunity to really develop the tools and see things from best in class, right? So Intel is best in class in manufacturing, right? And what I learned was supplier development, supplier quality, real good process development, starting with your metrology and MSAs, gauge R&Rs, and then working in a process characterization. So, obviously Intel's making millions and millions of chips a year. And if you're building a component that's tied to millions and millions of chips, that's hundreds and hundreds of millions of dollars, right? So, it's not a regulated environment like defense or aerospace or medical device, but it's regulated with cost. So, which is probably more brutal than the other three combined paperwork wise, right? So I really learned how to characterize processes, right?
I have heard, and I've never worked at Intel, so this is all secondhand information, but I've heard that it can be a pretty intense work environment. You mentioned that if you have an opportunity to work at a large company, then you should do so, even if just for a short time, because of what you'll learn there. Do you feel like the volume of knowledge that you obtained at Intel, was that primarily just because of their really refined and wonderful processes, or was it because you spent a lot of time working there and what one engineer might spend, you did 1.5x or whatever, so naturally you're going to learn a lot more there?
No, I think the way to look at that is think of it as an uphill and a downhill. There's companies that are in their sweet spot. When I was there from 97 to 2010, that was the heyday, right? Stock was splitting in 96, 97 like crazy. People becoming millionaires, right? With stock splits, right? So you have a company in its prime, right? Now compare that to some of the big aerospace companies, maybe some in Phoenix, that are well past their prime. They're on the downhill slide. They're chasing cost, right? And cost savings. So, if I would rephrase my thing, if you could work for somebody in their zone, in the prime of their business model, you do it because their tools and their training, you're going to spend thousands to get that on your own, and you're not going to get it. The stuff if at all, the stuff I learned in Six Sigma or statistics or design of experiments and gauge on R's at Intel is best in class in the industry, right? So, you take that, it's totally transferable skill set.
How about at Medtronic, another very large company? What did you learn there that you were able to apply in the future?
Yeah. So fascinating thing, right? This great Harvard case study out there, something about, 3 tools or 3 types of differentiation. Maybe it's Tracy and Worsama, or maybe it's the white paper, but I encourage everybody to read it. It's a quick study, but they talk about technology leadership, customer intimacy, and operational excellence. And if you're going to be great, you got to pick one and be great at it. Right. So Intel was technology leadership. Medtronic, I thought was technology leadership. And then I got in there and I realized it was not. They were quite bad at developing technology. That's why they acquired a lot of companies. But they were very good at customer intimacy through the sales force to the doctors. Right. So if I told you that as an engineer and you were a technical engineer, you would modify how you try to fit in on day one at Medtronic. Nobody cares that you're an engineer and you're technical. You better be good with people.
Interesting. What are some behaviors or strategies that you picked up when it comes to customer intimacy at Medtronic that maybe other people listening to this can learn from?
Yeah, I think there's a big area, NLP, neuro-linguistic programming, rapport building, some great professors out of Stanford, on how to build rapport, understanding rapport, how to see rapport in facial expressions, 142 positions for lips. So calibrating with your audience, see, you just changed your lip, right? So that's an inquisitive face you just made, right? So there's things that you can become very in tune with that help you calibrate to the feedback mechanism as you talk and you see from the person. Did they like that? Did they not like that? Are they uncomfortable? And being able to modulate. So I really worked at that at Medtronic because it was a finicky cross-functional product development team.
That's a really interesting way to look at it. I mean, thinking about facial expressions specifically, some people probably just kind of organically pick this up, right? Throughout life, they have experiences, they see enough faces over time, and they kind of pick up the different facial expressions. We all do, right? To different degrees. But looking at it from an engineering standpoint and say, oh, there are 142 lip positions, lip configuration, something like that. That is such an engineering way to look at it. Here are the 142. This is what one means. This is what 38 means. And
you can teach it, right? You can teach. I think it was like, the book was maybe leading with rapport with integrity, leading with integrity, or gaining rapport with integrity. Because once you see that, it's kind of like cheating. Like once you're really good at it, it's kind of like cheating, right? So with integrity is using it for the betterment, right, of everybody. But, it's an interesting thing, right? Because if you're listening, that's one. But you also have to be looking at people, right? So in engineers, you need to look at the person you're talking to. Because otherwise you'll never get their facial expressions, right? So stop looking at your shoes and look up. And there's a lot of feedback that you can and should be picking up body language wise.
Let's talk a little bit about Minitab. This is something that we haven't talked about. A tool. It's a tool, a very specific niche tool for using statistical analysis, but it's something that you've used quite a bit in the past. Can you share a little bit about how you've used Minitab? And maybe we don't focus so specifically on that particular tool because there are other tools to use for this sort of thing, but how you've used it in integrating data analysis and kind of what that process looks like in the context of quality assurance.
Yeah, so high level, Intel, most of the semiconductor companies use JMP. That's made by SAS out of North Carolina, right? And that stands for John's Macintosh Program, right? We built it in the 80s. It was very easy to use, right? So back in the day, 15, 20 years ago, you could write a script in Jump, right? Hey, I got 10 columns of data. I'm going to write a script and I'm going to run these scenarios on those 20 columns of data. And this is the output I want, right? Minitab has never allowed you to do scripting. So to this day, they've really made some advancements in the last, version, but to this day, they're extremely far behind in a lot of aspects. But Minitab is big in the medical device industry, right? What's nice about Minitab is it's in between Excel and Jump, right? So for I call it the 4-speed transmission, right? And Jump is a 6-speed or a 7-speed. Right. So for the average user, Minitab is very easy to use, very digest. They got great online videos, how to use Minitab to do statistics. And you could watch 40 hours of video and you could get up to speed. Right. And you need it.
Yeah, I'm sure you do. Is there a real world example that comes to mind you can share where you used Minitab in order to do some kind of data analysis and what was the result of that?
Yeah. So one of my big takeaways when I was at Lowell, we built a Minitab add-in and we filed a patent on it and it was called PQIT, PQ-IT, like PQIT, anybody in medical device, you understand IQ, OQ, PQ, right? So PQ has 3 lots of data traditionally, but you may have a machine part that has 20 features, right? So now if you have 3 lots of 20 features per part, that's 60 columns of data you have to run through analysis on, a capability analysis, check for normality. And in Minitab, there's no easy way to script that. There's some end arounds, but in general, most people hack through that one column at a time, right? And it's just methodically painful, pound your head on the wall, painful. So I had a programmer in Minnesota. I mapped it out, and a guy named Mike Mercer, a complete Minitab rockstar here in Minnesota. And he built a custom macro that will do validated data analysis for up to 300 columns of data. So you could feed it 300 columns of data. You give it an Excel template with the upper spec, lower spec, tolerances, because it needs that for the analysis. And then it'll crank out the complete analysis, build you a summary table, and put all of the graphic supporting data into an appendix and put it in Word format and PowerPoint format for you. Right. So, it's gone on. And since I've left, they've presented it to some of the big OEMs and the big, head statistician of some of the big medical devices where, hey, this would replace 10 people in my organization because you have every supplier quality engineer crunching data manually. And I did it. I did that at Medtronic. So I knew exactly the pain points from doing it for all these validations. And it was 40 hours of work to do a validation. Easy. Right. And now I knocked that down to 15 minutes with this macro.
Jeez, that's incredible. I remember using it in college, and I remember it was pretty straightforward to use. I probably just barely scratched the surface of it, but I know that we would do things with DOEs, designs of experiments with it, and it was super useful to use. And, we learned the DOE process by hand, right? Kind of going through all the calculations by hand. So we understood the basis for it. And so I remember going through and using Excel and doing that and then being introduced to Minitab. And I was like, wow, this is so much easier and so much faster.
Yeah, there's a lot of great programs. Since I started SINE18, not all my clients have Minitab or Jump. Some of them don't want to spend the money. So I've had to branch out into a lot of these Excel add-ins, right? And which I viewed kind of negatively, to be honest, before, because why would I ever do that when I could use Jump or Minitab? It's like, why would I drive my Crown Vic if I could drive the Porsche that Dad has in the garage, right? Like,
of course,
you wouldn't, right? Until you need the Crown Vic because your client has a Crown Vic and you want to fit in. So there's some great Excel add-ins for those out there that are looking. SPC for Excel is fantastic at $300. For those really big and continuous improvement, QI macros is fantastic at less than $400. And then Sigma XL, is really, really strong. And it comes with a Monte Carlo simulator inside of it called Discover Sim. And that's probably about $1,000. So for those bootstrappers out there, you could pick up one of each. And they overlap. They're not all the same program, and they overlap. And you really can do, Sigma Excel can do everything Minitab does. In a lot of sense, it does it better.
Excellent.
So for anybody looking for a Minitab alternative that doesn't want to do the painful annual license subscription model, you could buy a standalone copy, and it's $800, something like that. It's fantastic.
That's
terrific.
John.
Okay, I know all three of the owners from the companies, and I'm helping each of them put in some of the orthogonal metrology matching code that we need, and we'll talk about later on today. But a lot of them didn't have it, so yeah, I have access to some of the top guys at these companies, and they're fantastic.
Very cool. Well, those are some very actionable steps. Those of you listening to this and thinking about getting into statistical quality control, those are some perfect names that you can go research and get into. Let's see, Edward, you have some pretty good experience, maybe kind of unique experience collaborating with OEMs and suppliers. Can you talk a little bit about some of the common pitfalls? Because if you're in engineering, then ultimately you're trying to make a product, right? Whatever that product is, 99.9% of engineers out there, they're the final output of what they're working on is going to be some kind of product, whether it's in aerospace or semi or medical or consumer products, whatever it is. And obviously that requires supply chain and negotiating with suppliers, establishing relationships with suppliers and working effectively together. Talk a little bit about how you did that and especially some of the common obstacles or pitfalls that those listening who have to work in those areas should keep an eye out for. Maybe how can they overcome some of those challenges?
That is things that get my blood moving and pumping is supply chain management, supplier quality, and doing it to really create a core competency or an excitement feature, right? So there's so much here. So one of the things that I would tell you to the engineers out there, number one, your drawings are wrong. They're wrong. And your GD&T is lacking. Until you're a senior level GD&T certified expert with 5 years doing it, and you know how to run the CMM and inspection, and you know how the statistics play, just assume your design is wrong. Any of your readers or listeners, you give me a drawing, I'm going to find 5 errors, right? I'm fluid in GD&T. So, that's the very humbling thing when dealing with design engineers is you have to break their ego first. Right. And a lot of them in a lot of companies, and Intel was one of them where they thought their designs were perfect. Right. So one thing Intel did very well was design reviews. So I, as the person leading the design review, let's say you're the design engineer at Intel. I run the design review with the connector supplier, the substrate manufacturer. I run that meeting. I meet with you beforehand, and then I give you the floor, and I have you take us through the logic and your design intent of your design in your mechanical drawing, feature by feature by feature. Right? And it's painful. And this is where a lot of people are just, frankly, they're too lazy. If there's 50 features on the drawing, you had a decision process to put them there. I want to hear your logic. Right? And then the supplier is going to get to ask questions, and then we're going to talk about how are we going to measure that? Can we even measure that? Can we measure that and pass a gauge R&R? Because if we can't, we're dead in the water right now and MPD stops. At Medtronic, you couldn't move on until you passed the gauge R&R. So if you as a design engineer design something poorly or put a ridiculously tight tolerance and they can't measure it with the equipment that they have, you're dead in the water. Either you're going to wait 6 months for them to go order and install and validate a new CMM or new inspection equipment, or you're going to send it out to some other lab. And so really that's my first punch. That's where I knock out 90% of the people from the R&D side is they just don't understand that as part of the integrated product development phase. So getting good with a Excel-based feature discussion. If the listeners take one thing out of it, look at a simple drawing you have, and they call this, APQP in automotive. If there's a feature on the drawing, you need to have the nominal, you need to have the lower spec, the upper spec, and then if you should have some datum reference frame, logic. talked about. And then on the right-hand side of that, then we're going to talk about the gauge R&R and the equipment that the supplier is using. Does it meet the rule of 10? More advanced things of what's the total uncertainty. It blows out to 20 to 30 columns for each thing. And the key thing is, if I'm running a design review for you and your company, until we can answer all 30 of these dimensions and the notes, the supplier's not on the same wavelength with you. And a lot of people, visual inspection criteria, that's a black hole. Surface roughness, how are you going to do it? You're going to do it with an attribute EDM scale. Are you going to do a laser profilometer? You're going to do a drag profilometer. Surface roughness, color, Pantones, very vague quality characteristics. And everybody, they're painful, so everybody wants to skip them. And they come up, once you get to a validation and somebody fails it, then it's like, oh, we can't just skip it. And now you're delaying because it was hard. So people want to take the easy way out and just assume the supplier knows what they're doing and you're going to get the same thing. And it's never the case.
I have two follow-up questions for you. One, most engineers don't possess that level of expertise in GD&T, in quality control. Most engineers can put together a drawing, and as you pointed out, it's probably wrong. So what can engineers do? This is question number one. What can engineers do? Who can they turn to? What's a resource they can utilize if they know they don't have that kind of expertise? And then the second question is, what types of products or components require or can be justified? You can justify this process that you mentioned, because it can take a lot of time and it can be really expensive. Is it warranted for, every product out there that you're making, or can you narrow that into a more specific window of this type of product? It makes sense to do, but for things outside of this, you don't need to.
Yeah, that's a great question, right? If I lived down the street from you, right, and we could spend all this time talking about the nuance verbally, GD&T is a symbolic language, right? And if you're in a worldwide global supply chain, it's a must. It's 100% mandatory, because a guy in China or Japan or Germany can pick up your drawing and understand, there's some differences in the ISO version versus the ASME version, but they can understand the logic and the symbology, right? If you don't need that because the person in your supplier is right next door, you can get away without doing it. We certainly had people when I was at Lowell. After I left, one of the people came in from the OEM and said, "We're going to get rid of the GD&T. We have suppliers that think it's too expensive, really, because they don't know how to do it, and we're going to get rid of it." Not on some of the drawings. And once you get rid of it, now you go back and there's a lot of ambiguity that it creates, right? GD&T, it seems complex until you get trained in it. And then it's very simple, and it really prevents people from doing whatever they want. Still flexibility, but it gets rid of 85% of it, right? If you know it and I know it, you can send me over the drawing. I'm looking at him going, okay, he's got datum A, he's got a datum B. Like, I can understand how he's going to put this or mate this to another component. And he's telling me where to set up, the 000 and where the dimensions originate from. Like, I kind of get it. So based on that, I could come back to you and say, hey, listen, here's how I'm going to fixture this thing. Here's how I'm going to measure this thing.
Great. Well, let me take a short break here and share with everyone that the Being an Engineer podcast is brought to you by Pipeline Design and Engineering, where we don't design pipelines, but we do help companies develop advanced manufacturing processes, automated machines, and custom fixtures, complemented with product design and R&D services. Learn more at teampipeline.us. The podcast is also sponsored by The Wave, an online platform of free tools, education, and community for engineers. Learn more at thewave.engineer. Today we are privileged to be speaking with Edward Jaeck, and I'd love to talk a little bit, Edward, about what you do at SINE18 in terms of strategy consulting. So we touched on this earlier, and can you kind of walk us through the process of how you work with new clients, developing a strategy for them? This is probably like a pretty broad question, probably too broad. So maybe you can pick a kind of a niche within that question and walk us through the process for setting up a strategy, keeping in mind that the engineers listening to this mostly are not leading a business. They're working within some other business. And so it might even be, how do these engineers help their teams course correct if needed, or suggest proper strategy if perhaps they're not on the right strategy right now?
Yeah. Great question. Very easy answer, actually. But I will give kudos to Jeff Luftig from CU Boulder. He was the professor that really brought this home. He was an expert in strategic policy deployment, ocean economy planning. So one of the classes we took, we did all of that fun stuff, and then kind of picked up another thing, construct analysis. And then you combine that into kind of I call it the Reader's Digest version of a strategic plan, right? So strategic plans are like designed experiments, right? If you took a DOE class, in column 1, you had +1 and -1, right? And then in column 2, for every +1, you have a -1 and a +1, right? And then column 3, for each one of those, you had a +1 and a -1, right? So it's a 2 to the 2 to the 2, 2 to the 3. So strategic planning is the same concept, and I do them in Excel because you start with level 1 objectives. So for example, when I look at your website, I see automation, I see MPD, I see 3 to 4 areas that you're playing in, right? So I did this last night. So I jump into that. So level 1 would be, for your organization, grow. You want to increase revenues, right? And then you have a subset of that would be grow profitability. It's not how much revenue you bring in, it's how much profit at the end of the year.
Yeah. Right? How much do you keep?
And this is why you do strategic planning, because if you don't do that, your sales folks will sell ridiculous amounts of stuff to optimize their commission, but not profitability. Right. And they'll say, it's not my job. I don't control profitability. That's operations engineering. So I'm going to sell $100 million in revenue that chokes off the factory and it only makes 3% profit. Right. So as a CEO, if you're not managing that, you don't want feeder work. You want profitable work. Right. So, you have the financials always. You obviously, looking at your website, you pride yourself on culture. So you have a value at level 1 of great place to work. Right? Or awesome place, or cool culture, or family-oriented thing, right? And then you have a technology thing. So at your level 3, you say dollars, amounts, culture, and technology. That's your level 1. Now to level 2, now you got to break each one of those up into at least 2 subsections, right? So now you say, okay, technology. So now I look at it and say, well, what's more important for Aaron? Does Aaron really want to play in the automated space? Is he selling services? So I'd split your level 2 to be stuff we make and services. So hard items and services, right? So you want to improve services offered and you want to improve goods sold. Very generic, right? But you always got to look at your strategic plan as a CEO is you can't hand off something to somebody until you have defined it in sufficient detail for them to take it and run.
Yeah, right.
It's not their job to mind read you, right? And this is what a lot of senior leadership does. They're pie in the sky. They're aloof. They talk buzzwords, but they can't drill it down to the handoff in the 200-meter relay. Right? You have to come down far enough from the mountaintop. To me, your director of engineering, like, dude, I get it. I'll take it from there. Right? So, and you do this, you just keep breaking it down into level 3. So, okay, so now improve services. What do you mean by improve services? Well, we do MPD consulting services and then we do design services. Those are both very different. Right? One's softer than the other. You still have mechanical drawings and electrical drawings. Those have to be technically correct, right? So you've immediately split level 2 down to at least 2 buckets at level 3. Now at level 4, you can start handing it off to your director of mechanical engineering or electrical engineering and saying, hey, listen, you guys need to have correct drawings. You need to have correct stuff in your things. And now once we get to that level, we could add some KPIs, percentage of drawings going out that are 100% correct, right? Or percentage of drawings that go out that have 0 customer complaints, right? So It's funny when you do this, like I could do this with your company, honestly, if you were fluent in Excel, we could do this session in 2 hours. And the funny thing is once you see it, you'll never unsee it. And that's the why. Why do I do it? Because every time I do this with the CEO or an owner, they laugh and they say, that's so simple. And then they call back and like, hey, we're ahead of schedule. We're marching to the plan and we've already achieved 75% of our objectives, right? Because they've seen it.
It's the process of taking your business holistically, breaking it down into its constituent parts and continuing to refine how you break it down until you get to the level where you can start measuring things. You've defined things in enough detail that now you have KPIs. You can start measuring, putting metrics against these broken down subsets of the whole. And then once you have KPIs, well, now it's just executing and measuring against those KPIs. Is that a fair way to summarize it?
Yeah, it absolutely is. And there's a couple interesting things. Once you get to level 4, if I do this at your place, for example, I would do it on a whiteboard and I start level 1 on the left and I start working on the right. By the time I get to level 4 with you, it's starting to look like a work breakdown structure. And there's the next step is a Gantt chart. Right? So now let's say you have 3 things and each of the 3 things has 9 items, right? Now there's 27 items at level 4. They each have a Gantt chart and resources required. Now, if you're in the back of the room, you could look at that and now you start to see an order of operations. This is a machining term, manufacturing term, because you can start looking at it and say, well, I can't do that until I do the other one. Like at Lowell, I couldn't build my lab until I cleared my tool crib out of the space on the floor. So I don't know what it was, but the tool crib took up 60 by 60. That's got to go somewhere. Team figure out where that goes. It's like moving people for a dam. That's got to go. And then I start building my lab. So that's that aha moment for the strategic plan people. It's not like there's 20 different teams working in parallel independently from each other. You have 5 engineers that are doing everything, right? And there's a time order, right? So you have to figure out, and you can't see it until you see it on the same whiteboard. You see the natural flow of this becomes that, and this needs to be done before this, right?
That's a terrific breakdown. Yeah. Wonderful.
Right. So then you see it. And again, once you see it visually, it's seared into your brain and you can't unsee it. And then you just start subliminally executing to it, which is manifestation, right?
Yeah.
It's manifesting, right? It's not manifesting. You just put it out there to the universe and it's seared into your brain. Now it just starts to happen.
Awesome. Great example. You have some significant experience in the medical device space. We talked about Medtronic and your time there. A lot of our listeners are in that space, medical device development, working for med device OEMs. What are some trends in that industry that you're seeing and are excited about? What do you think that we're going to experience in the next, 1, 2, 3, 4, 5 years?
There's nothing that excites me in that space. The FDA just chokes off,
really
everything. There's nothing exciting. And I'm not an expert like Steve, Gompertz. I know Steve, he's in town here, and great interview you had with him, a couple weeks back. The regulated space, it's fantastic in keeping people safe. And Steve highlighted this. Their sole purpose is to keep patients safe from people making stupid mistakes or skipping things. And so I'm always excited about the FDA keeping you and your loved ones and me and my loved ones safe from lazy manufacturers or people that are chasing the bottom line. So I love that aspect of it. But as far as ingenuity and all these other things, it completely stifles it, right? Which is why you see big companies buying smaller companies. Smaller companies get through clinicals at a much lower level with the FDA than a Medtronic could ever get through. Right.
Yeah.
So, and that's kind of the way that the FDA seems to like to do it is don't let the big companies do it because we choke them out. Let the smaller companies do it. They get acquired. We can get rapid innovation out of the small, nimble companies. And then the big companies have to go through this rigorous process to make sure it's all there. Right. Which actually works pretty well.
That's a really interesting insight. I had never thought about it like that before, where larger strategic med device companies maybe have to go through more rigor in their FDA process than a smaller startup might. Is that something that you experienced at Medtronic?
Oh yeah. And then, we saw it at Lowell where I was the supplier, right? And, one of my things, I'm a validation expert, right? So if I'm at a conference, I'm holding court in the statistical IQ, AQ, PQ validation, how to do validation planning, how to do the data analysis and ways to streamline and pool to save time and money, right? So that's what I really dug into there, because that's really where a lot of companies get bogged down. Is they don't know how to validate it, or their drawings were poor, right? For example, going back to the drawing thing, if you have a cube, right, and you want to dimension it with length, width, and height, right, or a rectangle or something that's not equal to A equal to B equal to C, you could do that with 3, but those are individual features and they vary individually. But you could also put basic dimensions on that with a profile all over and you're done. Right? So, a profile is a great example of how GD&T simplifies validation because it's only one dimension. I'm going to give you this complex thing, measure that complex thing in software, and give me a profile. And that measures 20 features simultaneously.
So tell me, if you're not excited by anything in med device because there isn't enough freedom to innovate, which that makes sense, that's fair, what industries are you excited about?
I don't know if I can answer an industry that excites me more differently than others. What I can tell you, concept-wise, what excites me that applies to DOE, that applies to NPD, is design of experiments, right? And what they've done in design of experiments and how some of these new, for example, definitive screening designs by Dr. Knoxheim here from University of Minnesota and Brad Jones from JUMP, also Dennis Lin had a lot of input into that. These new and innovative design of experiments, that to me is my passion. When I go to a high school here, and I did last January, and I bring the catapult experiment with me, and I give the catapult to the students, and this is an engineering class at Shakopee High School, and you say, here's 11 poker chips, Aaron. You've got 11. Every time you run a shot on that catapult, you got to give me a poker chip, right? And they do it one factor at a time, like we all did in college. Right. And I say, here's the distance that I want you to hit. And you got to put a piece of tape out on the floor. And I gave them 11 poker chips. I said, I got 11 shots. Right. And they barely could figure it out in 11 shots. They spent like drunken sailors. Their money was gone within 10 minutes. Right. And then I took another 2 people out of it and I showed them the concept of design of experiment, define the input variables, what are the ranges, min max tension on the rubber band. Engineers picked that stuff up pretty quick. I showed them the concept of the DOE. We laid out a Minitab and I ran a 2 to the 3 full factorial. That's 8 runs. We ran 3 center points. So that's 11 runs. Within 11 runs, they mapped the entire range of those input variables and they had an equation that mapped everything from low setting to high setting on all 4 or 5 variables. Now, to show that point, the teachable moment is when I move the marker on the floor and say, great job, team, you've now hit 20 centimeters out. Now I want you to hit 62 centimeters out. And you have to hit it the first time, right? The beauty of running is, why do you run a DOE? Because you can go back to the DOE, go into the equation, use the optimizer tool, set 62 as the output, and it'll tell you what settings to use on the input parameters to hit 62 centimeters. So we did that. And I said, okay, this is what the DOE software is telling us based on the experiments that we ran that covered the range of all of those inputs. We have everything mapped here. We can hit everything in this field of view. And they put the little tennis ball spot on that piece of tape within a quarter of it on the first shot. A
beautifully tangible example there. I love that.
Teachable moment.
The first team would have to go through that whole process over because they're basically doing trial and error, right?
Exactly.
Whereas the second team, like you said, now they've got it all mapped out. They have an equation, basically, an algorithm that they can plug variables into and export the result at the end. That's terrific. That really solidifies the value and usefulness of DOEs.
Yeah, and it's not always as simple as that, right? Life gets complicated quickly.
Sure.
But the concept is very important when you're sitting with design engineers with egos. Because you and I could look and say, Aaron, can we agree that we're not going to get this design right on the first shot? Yes. Okay. So we can kind of say, well, the automated machine, we're going to let it range from 10 electrical units to 20 electrical units. We're going to run the other thing from this, this mechanical setting to this mechanical setting, and the tension is going to be from A to B.
Yeah.
Okay. That's for 2 parameters, 3 parameters, 2 levels. That's an 8-factor DOE, full factorial. If maybe there's a center point, you run it. And we know very quickly whether we're in the space or we're not in the space.
Yeah.
Right? And if you're not in the space, go change your design. It's bad.
Right. Yeah.
Right.
Well, just a couple more questions here, and then we'll wrap things up. You had sent me some material prior to our interview, and one of the concepts or terms that I had not seen before was metrology matching. Can you talk a little bit about what is metrology matching and how can engineers use that in manufacturing?
Yeah. So one of the things, I'll start backwards. Why would you do metrology matching? Metrology matching is required if anyone's going to go dock to stock with a supplier, right? So that's a supply chain term, purchasing term, right? If Aaron's going to ship me components to Edward Jaeck SINE18, you got to make sure that you're measuring the same thing I'm measuring, right? So I could trust your measurements. So how do you do that, right? So when I was at Intel led this by doing a very detailed, here's the way we measure at incoming inspection at Intel. Right. And here's the work instruction, and here's the pictures, and here's the fixture. And then I would send that to Aaron. And if Aaron has the same machine that I do, he could just take that program and that fixture, and your outgoing inspection is up and running. You do your gauge R&R, right? And you and I are communicating weekly, and we iron that out. Now, that's where the MSA manual stops, right? Or the automotive thing stops. The most important thing, though, is to actually build units, and you need to measure those units, and I need to measure them. So how you do this is you would understand this, you build SKU samples. So let's imagine you're making a rod 1 inch plus or minus 5 thousandths, right? If I ask you for 30 samples, you're going to put them on your lathe, and you're going to build me some that are so ridiculously tight within one batch that they're useless for metrology matching. What I then tell you is, Aaron, I don't want one pile of tight things. We need variability inside the spec limits. So I want you to change the drawing and put different nominals on that drawing that span them out. I want 10 piles of 3 parts each that span the lower spec to the upper spec. Right? So if lower spec is 0.995, I want the nominal on drawing 1-1 to be 0.995 plus or minus something tight. Right? And we're going to get a pile there. Then we're going to get a pile up at 1.005, right? And then we're going to get a pile at 1.02 or 002. And we're going to break that spec range up into 10 separate piles, right? And then we label them, parts 1 through 30, right? Literally either on the part with a laser or machined in or with a piece of tape or into a canister. You measure part 1, I measure part 1, right? And now in Minitab, that sets you up to do a paired t-test, because part 1 is measured by you and me. It also sets you up to do a thing in regression analysis called Deming regression. Deming regression is a little bit different than ordinary least squares. You have a lambda term, and if lambda is equal to 1, you get this other term called orthogonal regression. If the slope equals 1 in orthogonal regression, you're saying the same thing I'm saying, right? You measured it's 1.01, I measured it's 1.01. If you're getting a bias, then you can see that slope, right, on the XY axis, you're going to get a different slope, and you're going to get a different intercept, right, if there's a bias. So that's what it does. There's no software out there that's doing it as a GUI. Jump doesn't have it. Minitab doesn't have it. I'm working with these 3 Excel providers to build it in this Excel add-ons, and I'll probably work with Mike Mercer to build it in Minitab. Right.
Nice.
But what it basically does is it tells you, is there a statistically significant bias between Aaron's outgoing and SINE18's incoming? Or are these 2 things statistically the same? And even if they're a little statistically different, are they technically equivalent, right? Or practically equivalent, which is some ratio of that delta to the total spec tolerance, right? It's like, dude, you're in the noise, shut up, we're moving on, right?
So does that just go back to an agreement, I guess, between a supplier and the receiver that, yes, I, as the receiver, agree that what you as the supplier is sending me agrees with what I expect it to be and what I'm measuring on my end?
Yeah. Because if you don't do that, you're just out in left field. You're measuring in Phoenix and your lab is not temperature controlled, humidity controlled like my lab is. And you're getting something bigger and I'm getting something smaller. Apples to oranges. Who's right? Well, everybody's right and everybody's wrong. Right.
Right.
So that's where the OEM, to me, I'm passionate that if you're the OEM, it's your job to tell the supplier exactly how you're measuring. So when I was at Lowell, I would push that back to the OEM. Like, if you don't know this better than we do, and you don't have a lab better than we do, and Lowell had a world-class lab, then who's leading this dance? Right? If you're better than us, then you lead the dance and send me your fixture and your work instruction. I'll have my team do it. If you don't have that capability, like a lot of these medical device startups don't, then we could do that and send them what we did. Right? And they could then use that, right? So you kind of figure out who's better at it. And sometimes you're better at measuring this feature and I'm better in measuring this feature. And then you learn from each other.
Yeah. So, okay. Metrology matching 101. There you go.
Yeah, that's the Reader's Digest version of it.
SINE18, if you want to dive deep into it there.
Yes.
Well, let me ask you one more question and then we'll wrap things up here. I'm super interested in how we can accelerate the speed of engineering. I think I look around us and I see pretty much everything that we interact with came as a result of an engineer doing his or her job. And it brings a lot of joy into our lives. I mean, think about the medical devices that are life-saving, right? Or just the vehicles that we drive and go to work every day with, or running water or a stove to cook food, whatever. All of these things have dramatically enhanced our lives for the better, for the most part, for the better, right? We could probably find some outliers in there that we don't love so much. Social media. Anyway, moving on. What is one way that you have seen teams accelerate the speed of engineering? Anything tangible, tactical that you can point to?
Yeah. So I have two. I have a great guy in town here. He's big in rapid prototyping. So one of the things now that you can do in some of these 3D printers is you can bring color in, right? So, one of the things I do in product development is if I had a part, for example, a CAD file, and you're machining it for me, right? What I would now do is I have a prototype. I'm holding it in my hand, and in that prototype, I've really thought through where I want that part measured, like to create the diameter. So I had Steve, or Austin, he built a prototype to where now if I want you to measure the top Z height, I had him put 6 orange spheres on the top surface, 12 o'clock, 6 o'clock, 3 o'clock, 9 o'clock, and in between. And now I can send you that object and say, Aaron, this is where I want your team to measure that top surface. 6 places, 12. And you're looking at the part with the color things. You're like, oh, this is easy. Okay. And now there's a diameter, there's a bore, and there's 2 different Z heights, and there's 6 green circles at 2 different Z heights in that bore. Aaron, here's how I want your team to measure that bore. 2 levels, 6 hits per level, right? Now you're looking at it visually, right? So that saves all of this back and forth in the beginning. And using prototypes, what I did at Intel was I used prototypes to actually program the machines. Yes, they're not perfect, but they're close enough for your CMM to start the programming and the hits and get the program and have that done from a project management. It's now being done in parallel, not in series. So that program is 90% done before the first article ever comes off your CNC machine.
Yeah.
Right? The quality team has to be running in parallel to you in the machining side. So when it comes off, their program, they've played through 90% of the bugs. And now when you get that first part, it's really just fine tuning their program and they hit it quick. Right? A lot of things have to be taken out of in series to be put in parallel. Right?
So I guess the high level principles look for opportunities to go from series to parallel.
Yeah, a lot of things in project schedule. When I did projects as an integrator at Intel, that's how you reduce everything. You have to decouple it from series, right? And you bring them in parallel. And that doesn't mean it's going to be 100% complete, but you have to take the majority of their work out and put it in parallel, right? Or anybody
Great.
that's played a Microsoft project, they get that.
Perfect. You said you had two. What was the second one?
Yeah, a while back, I wrote an article for probably MD and DI magazine, and it was critical feature confirmation. And this is what a lot of design engineers can think through. So I think my example, if you just had a pipe, right? Let's say you have fluid flow through a pipe, you could understand the equation for fluid flow through a pipe. But if that pipe also had to deflect, right? So, deflection is now a function of d to the fourth, big D to the fourth, minor diameter, small d to the fourth, right? So you have deflection to balance with fluid flow. You want to optimize fluid flow, but minimize deflection, right? So putting those equations into a table now realizes that some things want to go the same direction, and that's easy. But now a lot of times they're competing with each other. They want to go different directions. Right. So then what you could do is you could build skew samples and you can test those, which is again a DOE concept, much going back to Taguchi designs. And if you build that logically as a skew set and you test them and there's no statistical difference with those outputs, those tolerances that you ranged, none of them matter, which was Taguchi's concept of robustness, right? So now it can't be critical. So for those in the medical device, this is how you get through designs quickly, because you can run some of these skew samples up front at the upper spec limit, at the lower spec limit. And when they don't throw a signal in the output, you say, how could they be critical features? Even when they're at their worst case, they don't make a difference to the output function. It's robust. We're in the linear zone. Stop talking to me. These are not critical. We're moving on. Right? And that in a medical device saves a tremendous amount of time. Because you don't have to do a gauge R&R on it, and you don't have to do an IQ, OQ, PQ on that feature, and you don't have to build three lots of parts and measure all those features, which is a lot of times a waste of time.
Terrific. Great. All right, Edward, I think, we've covered a lot of ground today. Thank you so much for being on the show. And how can people get in touch with you?
Yeah, so my website is SINE18, SINE18, like sine of 18 degrees, SINE18.net, N-E-T. And you can reach me by email at edwardjaeck@sine18.net. If you want to contact me, the other way really is just reach out on LinkedIn and send me a note that way, and then we could figure out how to do it. But for more on the company, go to sine18.net and see what I do and some of the testimonials. And
wonderful. All right. Well, thank you again for being on the Being an Engineer podcast.
Yeah, thank you for setting it up. It's been a pleasure, and always here to help others achieve more and skip the hard learning lessons that I had to learn the hard way. So happy to share the knowledge.
Awesome. Thank you.
Great.
I'm Aaron Moncur, founder of Pipeline Design and Engineering. If you liked what you heard today, please share the episode. To learn how your team can leverage our team's expertise developing advanced manufacturing processes, automated machines, and custom fixtures, complemented with product design and R&D services, visit us at teampipeline.us. To join a vibrant community of engineers online, visit thewave.engineer. Thank you for listening.